version of that.
Send it to me. Send me the link. Oh, apparently, apparently there's a Jimmy Barnes version of that. That would be awesome. It's on YouTube. Can someone please post the link? What I did was I discovered that John Howard, bless his heart, before he left, passed a rule saying that every member of Parliament had to make available to all their constituents that were interested in it a CD and a DVD of the National Anthem. So on Friday I went to my local member and I got this. They'll also give you a flag if you want one. A real flag. And I got a CD of the National Anthem, and I got all this really interesting stuff like the sheet music for it, and pictures of flags, all flags about Australia and how good Australia is. And here's some more stuff about Australian flags. I'll have a look if you want. And Australia's national emblem, and Australia's national colours, and Australia's national smell, and Australia's national sound, and Australia's national clothes. It's just all about Australia. It's wonderful, and I just really like it. And I know some people, dare I say communists, would claim that this national anthem of ours is a bit boring and doesn't really mean anything and contains the word "girt" too many times. But I say to you, fee to you, because it's stirring to hear a national anthem. And on Wednesday, at our Wednesday lecture, when we answer the question, what is a good programmer, it will be based on the national anthem answer. Yeah. Yes, there's a big link between what makes a good program and the national anthem. And if anyone is able to work out, because there is, I think, I had a big talk with my wife about the national anthem, because you know it was nearly Waltzing Matilda, which is a cool song, but we decided to go for a more boring, safe song. And I was talking with my wife and saying, national anthems are funny things, aren't they? What would you, if you could have your say, and any song in the world could be the Australian national anthem, what would it be? Working Class Man. Working Class. We had this great time thinking of songs. Now, if anyone can actually work out the song that would be my replacement for this song, and it's hard to replace this song, I will give you 2 brownie points. 2 brownie points to the person that can work it out. I have given you a clue. Now, in fact, I'm not going to say any more than that. Shh, 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 shh. Let us return to the lecture. Brute force it. The first person to get it, and I think only one person will get it, will get 2 brownie points, because I think that's the hardest and most interesting question of this semester. Now, a file is where we store data. And you might have noticed in all our programs so far, we haven't fooled around with files at all. And you might be thinking, don't programs always fool around with files? I mean, you have to store stuff in a registry or something like that. You need with C to be able to access a file. Well, how can C be said to do anything? So I thought, let's start thinking about what a file is. Now, you guys all know files because you've created them and deleted them and lost them and tried to undelete them. And you're very familiar that a file is like, well, what is a file? Well, now we come to it. I'm not really sure. Someone tell me, what's a file? Yeah, shoot.
A stream of numbers.
A stream of numbers? I like the description of that. It's almost poetic. A stream of numbers. Okay, yeah.
I know. Something you can access through all the file functions.
Something you can access through all the file functions. That seems almost circular to me, Richard. You've moved down one peg. No, don't be harsh. Don't be harsh. He's still very high up on the pegs. Yeah. Yes. Okay. The literal, physical, original file was something you put bits of paper in, or a rough bastard. If any, or like that's like a file for metal. I'm not actually swearing. Yeah. Yeah.
It's data stored on a physical volume.
Data stored on a physical volume? Could be. A collection of data? I mean, really, if you wanted to think about it, there's different ways of answering the question. And one of them is, how's it physically stored? And one of them is, what is it? What does it mean? What's its, like, meta-meaning? You know, what's the point of it? Now, it's information. Yes, that's right. It's data stored in a file. It's a collection of data. So that's what it is. How's it physically stored? Oh, well, that's tricky. Now, in the old days, computers didn't have enough memory to store all the stuff they needed. And the annoying thing was when the computer was turned off, everything in its memory was lost anyway. So people thought, we need to have some way of storing things that's permanent, A, or persistent, and 2, we need to have some way of accessing more memory than we've got in our computer. So they invented punch cards, which were little bits of paper you punched holes in, and they lasted forever, and you could encode information on them, and they had a standard width, which I believe might have been 72 characters wide, or 80 characters wide, hence our style guide. Our style guide dates from the days of punch cards. We just keep using the same one. And they lasted forever because our paper and so on, and paper lasts forever. And they were in records that contained a certain amount of information, and a file consisted of a whole lot of records with perhaps a special card marking the end of the file. And then people invented magnetic tape. I don't know if you guys have ever seen those huge magnetic tape drives. I used to have to look after them at the IBM data center. It was my job every day when I went in was to vacuum the inside of the tape drawers and to oil and lubricate everything so that the tape drives, because they went at awesome speed and they didn't want the tape to snap. And how they used to work, I can tell you, because it's very interesting, was they had a big roll, like a spool up here, and the tape came down. They had a big take-up spool on the other side where the tape went back up. Oh, my memory's gone. I vaguely remembered it as being slightly different to this, but let's suppose it's like this. And now, no, shh. They had a glass door. Shh. They had a glass door that exactly was the width of, I don't know what you guys are laughing at. It was exactly the width of the tape. So the tape actually like pressed against the glass at the back and the glass at the front. And there were 2 glass walls down here like this. And the neat thing about it was that there was a little sort of vacuum in here. This was a low pressure area. And as the tape spun around, this sort of acted like a sponge or a spring, like a shock absorber. So little bits of extra tape would spool out, and then suddenly the take-up wheel would pick up. But never was the tape being taut and jerking between the two. Instead, it would just like move up and down. And as this wheel went faster, you know, it would go, okay. So it was very cool. Your mind is in the gutter. So there's tapes, and then there's discs. People discovered discs. You can store more information on discs. And if anyone's gone to level 1 of K17, who's gone to level 1 of K17? Who's seen the awesome discs on level 1? You seen them?
Yeah.
Well, tell them what's so awesome about them. No, you say. What, do you read the logo? They're big. They're big. Big discs from the library. We've actually stuck up on the wall on the level 1 lifts. But what's so cool about them is if you look at them, you can see little dings on them. And they're actual physical head crashes, where the head's crashed into the disc. If you have a look at it, it's just like, it's got a little patina of dings all the way around. So go and check it out on level 1. So how a disc would work is, well, it's not like a tape. How do you store data on it? Well, it divided it all into segments, and then it put tracks on it like a record. I guess people were thinking of the old days of records. They weren't in a spiral, they were concentric rings. And then there was like sectors, and then a disc would read a whole chunk at a time, and the head would move in and out. And sometimes a head crash would occur in a sector, and you'd lose that sector forever, so the disk would remember not to write to there again. So it would have a separate table somewhere it's stored, and if you had a file that didn't fit on one sector, it had to go over several different sectors. Maybe it was a 7-sector long file. Some of it might be here, some might be here, some might be here, and some might be here. And it would say, this file is this sector, this sector, this, and there'd be something like a file allocation table or something like that that told you how to join all the sectors together and how to skip bad sectors and all this sort of stuff. And essentially, a programmer was isolated from that because a programmer didn't have to know how to access a disk, because who looked after that for it? Because accessing a disk was so complex, and all we really wanted was a bunch of numbers off the thing, a file of numbers. We wanted to get the numbers off. We didn't care about sectors and bad sectors and segments and moving around and allocation tables and fragmenting and defragmenting. We didn't care about all that. So who took care of that job for us? The operating system. In fact, the first operating system that came out on PCs was called PC-DOS. Or MS-DOS. Depending which flavour you got, that was the same. And, or more or less the same. What's the D in DOS stand for? Disk. Disk operating system. The whole reason they gave you an operating system with the personal computer was they figured that users could deal with just about everything, but having to understand how a disk worked was so complicated, we actually needed to have an operating system so people could use disks. So the operating system supplies things which let you open a file, read data from a file, write data from a file, and it all happens transparently under the hood. What's that an example of? Abstraction. Thank you very much. Abstraction. It's the first and most important example of abstraction we hit in computing. The abstraction of disks. And because disks were treated as an abstract type, that was really convenient because as bigger disks started to appear on the market, you could just use them as a user without caring, because it was the implementer of the ADT that just had to change the implementation behind the scenes to deal with bigger disks. You didn't have to care about it. Your program just says open the disk, read some data, write some data. And then we just stopped using disks. As well as disks, you can get USB sticks. You can get virtual disks. You can have a mount a CD drive. You can, there's hundreds. You can put it on your iPod. You can mount it over an NFS. You can do all sorts of things physically to represent the data in different ways. And you as a programmer don't care, because as far as you're concerned, it's a file. I'm opening the file. The operating system is implementing that icky detail for me. Can everyone see that? And that's really convenient for us. So really, it's almost an example of an abstract type. And in C, look how C does it. C is quite clever. They have a type called file, which they write in capital letters, F-I-L-E. And you're not allowed to know what that type is. It's supposed to be abstract. You can look it up and find out, but don't. And they're allowed to change that whenever they want. And if you want to access a file, well, how do we access our own abstract types? A pointer to a struct. Well, this file is actually a struct, and if you want to access a file in C, you need a pointer to it. So you'd go something like file/myfile. And that creates myfile, which is a pointer to a file. And now you pass myfile into the file functions, the interface functions, and they do all you want. And you don't have to care what a file is. There's a whole lot of file interface functions, and here are the ones that I think you need. F get C. F means file. It gets a character from the file, the next character from the file, the next ASCII byte, essentially, from the file. Up, yeah, off, forward, down. F put C. That writes a character to the file. F open. Why didn't I start with that one? That's what you have to do first. If you want to get a file, you have to open it. So you say F open my file. And that'll open the file for you. Oh no, you don't say F open my file. You say my file equals F open beyond .c. And the operating system opens beyond .c and calls it from now on my file. And you can pass my file into your programs and they'll do stuff. And it's beyond.c that it's linked to. So open, unless you specify to the operating system which file you want, and it opens it up and gives you a pointer to it. When you're finished with the file, what should you do? You should close it at the end. Because sometimes the reading and writing from a file goes through a buffer. And so things haven't necessarily been written out even though you think they've been written out. And when you say close the file, it tidies everything up and makes it all nice and neat. Have you ever pulled out a USB stick before you're supposed to? Yes. It's really fun, isn't it? Yeah. And the operating system says essentially, please F close the USB stick before you pull it out. And it's the same with this thing here. Use F close to close your files, because if you jerk them out suddenly, without closing them properly, data can be lost and everything can be scrambled. Fseek lets you jump around inside the file, and ftell tells you where you're up to. So one way of finding the file size, not portable, but it will certainly work in the operating systems you guys are using, is you can seek to the beginning of the file. Oh no, you always know the beginning of the file's position 0. You can seek to the end of the file, tell it to go to the end of the file. There's a special code for meaning the end of the file. Then you can say ftell, and it'll tell you how many bytes into the file it is, and that'll tell you the size of the file. Not always guaranteed to work, but it will on the operating systems you guys use. Okay, so I expect you guys should go away and look these up and just practice using them to open and close files and read and write. You can also read and write ASCII text to files using scanf and printf, fprintf and fscanf. Instead of reading from the keyboard, you can read text from a file, but it's got to be an ASCII file. Instead of printing stuff to the screen, you can print that same stuff to a file. But if you print 7, if you fprint F7 out, you're printing out what would appear on the screen is a 7, and a 7 is going into your file, the ASCII code for 7, which isn't the number 7. Does that make sense? It's like 52 or whatever code is used to represent a 7. So I don't really want you fooling around with the ASCII stuff because that's a bit confusing. Just do the binary stuff, I think, is probably simplest. Okay, now we had a question from someone, from Alex North, in fact. It was a brownie point question. How could you make your stack infinitely big? We did our stack with an array. And now you suggested using an array before for a ring. It wasn't so good for a ring because we could delete stuff. But an array is a perfect way of storing a stack. because when you delete stuff, you always delete it from the end. And when you add stuff, you add it back to the end. So it fits nicely in an array. You never have to juggle things along and fill in gaps, because that gaps only ever appear at the end. So arrays are very nice for stacks, but the problem with an array is, of course, if it's fixed size, your stack can fill up. And Alex had a challenge question saying, how could you modify your type so your array never filled up? Now, you could make it a linked list, like we looked at just then, but I think a nicer way, and I think what Alex was hunting for, not a nicer way, but an interesting way, I think what he was hunting for is, let's just have a look at our stack. Our abstract type for a stack, I believe we were implementing as a struct. And the struct contained the data, or the contents, was that right? Which was an array, and a pointer to the top, which was an int, an index at the top. And this was like int, array of ints, or something like that. Yeah, there was a struct. Does everyone agree with that? Looked a bit like this. Int top. And that was how you were representing your stack. An array of numbers plus another number telling you where the top of the stack was. Everything's perfect except the thing can overflow. So maybe to stop it overflowing, you could store int max size. And you could, before you did any operations, check you weren't exceeding max size. But rather than doing that, Alex sort of asked the question, how could we just make it so our array grew bigger and bigger? Well, rather than resizing the array, which you could do, doing fancy stuff, one thing you could do is you could have a stack pointer. A pointer to one of these structs. This is called struct stack. Which goes to next, the next stack. See, you can sort of see what I'm going to do. And then when your stack fills up, just malloc a new stack and set this stack pointer to point to the next one. Does that make sense? And when that one fills up, malloc a new pointer and get that to point to the next one, and so on and so on and so on. And then you've got this chain of stacks. And then you've got to do delicate stuff like when you pop off, make sure you don't pop off the first one, make sure you pop off the last one. And when you push, make sure you don't push onto the first one, push onto the last one. And keep your eyes on your freeze and things like that. Yeah, and that would grow and grow and grow. And that's a bit like a file made out of a whole lot of segments linked together. A segment contains a whole lot of data in a file, and when your file's too big for one segment, the disk has to find another segment somewhere else and links them together in the file allocation table. Or you could have stacks linking together with pointers. Yeah, Rob?
How is that not a linked list?
Well, that's a linked list of stacks rather than a linked list of nodes. It's a chain of stacks.
It's like a stack of stacks.
It's a, is it a stack of stacks?
Yeah.
Are you going to... Well, I guess I mean, yeah, it is, it is. I was sort of thinking, because I'm a bit stingy with memory, probably when it filled up I'd make it really big, and then if it ever got smaller so that some of those end guys won't need it anymore, I'd probably still leave them in the chain. I probably wouldn't pop them off. So they'd be sitting there for when I grew out again. That space will have already been set aside. But yeah, you could pop them all off and get rid of them. Yes?
Okay, if you have like an access stack of like pizzas, you
Yes.
can't actually access the ones that are on the top.
Yes.
Unless you pop off the other ones.
Yes.
So,
But they're nice and warm because of the ones on top. Yeah.
yes.
That's another advantage of stacks. I made you laugh.
Have
Yeah.
more kids,
Yes, yes.
Why don't we say pizzas? Pancakes.
Okay, yes.
Anyway, we take a node from the last one, and instead of pointing to the next one, we point to the one before it. And
Yes.
then when we pop off, we say the top item is the pointer to the last one, and then we free that bit of memory. So all we have in the stack is
Yeah, you could free whenever you pop.
we have a pointer
Yeah.
to the top item.
Yep.
And then that top item inside it has a pointer to the one before it.
Yeah, yeah, yeah. That's a linked list. Yeah, that's a linked list. That's right. Yeah, so you could just do it as a straight linked list of nodes, and that would be absolutely fine. And you could free them as you pop them off. Can I just say, though, there is one slight problem with free. You know I don't like free because misuse it can cause all sorts of terrible problems if you free memory that shouldn't be free or you forget to free memory that should be free. And the compiler's not going to help you here. The other thing that's problematic is that sometimes free isn't really implemented very well in the operating system. And you go, operating system, free this memory. And the operating system says, okay, I promise I will. But whether it does or not, you don't know. So, if you've got so I like doing as much of my own memory management as possible. If I've got something that grows big and then small, rather than pop mallocing and freeing all the time, just because I'm nervous that maybe frees aren't doing anything, I'd probably keep this. Any ones I'm not using, I'd store somewhere or something. Yeah, but yeah, your idea's right. I'm not criticising your idea. It's a brilliant idea. Yeah, yeah, yeah. A linked list is a great way of doing a stack. But But a linked chain of stacks is sort of fun too. Okay. So what have we seen today? Well, we talked a lot about motivation at the beginning, and hopefully you're all fired up and thinking, oh, I'm going to work really hard on the assignment. I'm not going to be one of those old ladies halfway across the bridge. And then we talked a lot about abstraction, and I suggested that abstraction of data is a nice way of solving a problem, and we looked at maybe that's a nice way of solving Josephus. Then we talked about abstraction again, and we looked at it in an operating system and how file I/O works is a very abstract way of doing things. We looked at how to solve the infinite stack problem. We played for apparently no reason at all the national anthem. And then all I really wanted to talk about now was snake. Let's go back to snake. Does everyone remember the snake puzzle? Oh, where is it? Oh, now this is confusing. I'm just going to click on the schedule button, and that's going to make everything good. When did that happen? That happened a long time ago, didn't it? Snake, that was week 7. Is that here? Ah, here we are. The snake puzzle. Now guys, what you had to do with the snake puzzle was this. I said it was made up of a whole lot of dominoes. Each domino was a pair of numbers, and they were stored in sequence like this. The first number was the value that we didn't really care about, and the second one told you the address of the next domino. So this domino, what's the next domino after this one? The one at 10. Where's that? That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the next domino is this. What's the value stored for that domino? What's the next domino? 14. Where's that? Well, we did 10 then, so that must be 11, 12, 13, 14. So where's the next domino? 20. And I asked you guys to follow it, and we'll say we'll terminate when we get to domino number, what did I say was the terminal? 32, I think. Domino with the next of 32, we terminate. And I asked you to find the length of this. And this is an interesting puzzle and very hard to do without writing it down. And did some of you work out it had length 8? 36 is the end, is it? Okay, 36 is the end. Did it have length 8? I vaguely remember from when I said it had length 8. See if you can track that through. Because if you can track that through and get to the end and work out the length, what have you just done? You have just determined the length of a linked list. And the snake puzzle is really just a linked list. This is all a linked list ever is. It's a series of dominoes, or as we like to call them, structs. The simplest ones only contain 2 values. A value that you're storing at that location and the address of the next one. Put together, this is what a linked list looks like. Your question in the lab this week is to write an 8BMC length function that, given a grid of numbers like this, tracks it through and works out its length. How hard is that?
Easy.
Easy if you know 8BMC. How hard is it if you don't know 8BMC? Really hard. So make sure you know 8BMC because it's very, very easy. All you need to do is read 2 values, load one of them into a register, and presumably that's a register, and then using that value loaded in the register, that tells you the next value to load into the register. And you just keep looping. Using that value, that tells you the next one to load in. And you keep going along the list, loading, 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 increasing something by 1 every time, presumably another register. You've got so many now. You don't need to even keep it in memory. Increase by 1 every time until you get to the magic number at the end, 32. Now in C, when we have a linked list, how do we mark the end of the list? What address value do we say means end? Null. Reserved word. Null. Now reserved, because it's used all the time. You'll get it once you load in stdlib. Is it in stdlib? Pretty sure it's in stdlib. So to work out when you get to the end of a linked list in C, you keep checking to see if the next guy is equal to null or not. And if it's not equal to null, then you go to where the next guy is. And then you see if his next guy is null. And if that's not right, you go to the next guy and you keep repeating. Okay. Does everyone understand snake? Now the next puzzle I gave you, the other puzzle I gave you in this lecture was the triangle puzzle. Do you remember the triangle puzzle? Has someone done it? Did you do it? Yes. No, shh, don't say what it's called. Well done. Who's done it? Put up your hands if you've done it. 1, 2, 3. No one on this side? This side gets the Mars bars again. Don't show anyone what it is, but it's awesomely done. Because everyone can do it now, because I've showed you how to do file I/O. So all you need to do is create a graphics file. Every time you go to a point, set that pixel on. So you just need to know the format of a graphics file. What's the easiest format of a graphics file to program in? A bitmap. No, PBM. The PPMs. PPMs, I think. Even better than RAW. Oh, what's RAW?
RAW is just the bytes in the file.
Yeah, that's PPM.
That's PPM. It has a little header saying the dimensions of the graph.
With even no header, you load
But then how does it know how to display the dimensions of it?
you have to load into a program that lets you enter the dimensions.
Oh, no, yeah, but this is actually a format that will actually be, yeah. PPM is actually the raw data. So what you've got to do is you've got to Google PPM. Parts per notation. Oh, let's go to this, PPM. Wikipedia, free encyclopedia. That looks like a good place to go. Yeah, portable pixel map, that's what we want, graphics file format. There's lots of them, one for grayscale, one for black and white, and one for colour. Here's what it looks like. This is a file that you could save, and that's the letter J. Yeah. That's the black and white one. But you have to encode it, with 1 if it's black and 0 if it's white. And you have to initially say this is a P1 file, which means it's black and white, bitmap file, and you have to say the dimensions. This is a 6x10 file, because it doesn't actually care how you wrap it around. And you can put whatever comments in you want. So you could make this file and display it. And at uni, if your web browser doesn't display these files, PPM files, you can easily convert them to GIFs or PNGs or anything just using the convert program, which is on the command line here. You just go convert 1.ppm to 1.gif, and it'll turn it into a GIF or whatever you want. So the convert program will just change it. So that's what it looks like as a black and white one. That's a bit boring, but that's all you need to display the triangle. But you can also do a P3 file, which allows you to put colours in. And instead of putting a 0 or 1, what you put in is the colours. And the colours are going as RGB, and it mixes them up. So this is a file that's 3x2. The first one has 255 worth of red, no green and no blue. So what colour is that? If you mix together a whole lot of red and no other colours? Red. Our first pixels are red. Our second pixel is green. Our next pixel is blue. Our next pixel is a mixture of red and green. What does that give us? Yellow. Our next pixel is all the colours mixed together. That's white. Our next pixel is black. And now these pixels are obviously stupidly big. It wouldn't look like this if you displayed the file. They'd just be 1 pixel each. So you can make enormous files like this. Now, but instead of writing them out as numbers, write them out as bytes. And you can use that using the file. So if you wanted to, you can solve that triangle puzzle, which is really amusing, just by using a PPM file. So everyone should have a whack at that. And the last thing I wanted to say, and then we'll be able to finish early or ask questions if you want, was we were talking something about philosophy in the really interesting last lecture we did. Just briefly, we were talking about this issue of how would we know if we were in a simulated world or not? How would we know if this was the real world or we're just replicants in some simulated world? How do we know what's real and what isn't? And there's a lot of philosophers and a lot of computer scientists doing interesting work. Well, thinking about this, trying to work out how could you tell? And there's some ideas of ways you could maybe tell. Well, I reckon more likely even than being in a simulated world is we might not actually be here now. We might actually just be a video on YouTube. And actually, I suspect we are. So this is all just a video on YouTube. Now, we were looking at steganography, how you can hide messages in messages. And one of the interesting things people are thinking, if they're inside a simulated world, one way of telling we're inside a simulated world is maybe the creator has hidden some messages in this world for us. Like maybe there's Easter eggs. Or maybe we can find copyright messages. or maybe, you know, one of the people making the world, like in the Truman Show, is trying to sneak us a message telling us we're just simulated. And that's all very interesting. But I started to think on the weekend, what if we wanted to go the other way? What if you're inside a simulated world and you wanted to send a message out to the real world? So let's suppose that we're not in a real world, that we're just a Google YouTube video. And let's suppose that our creator is a guy called Patrick. And let's suppose we have to work out a way of getting a message to Patrick like, Patrick, please post the last 7 videos. Okay? How could we get that message out of this virtual world into the real world?
The question is, how do we know there's been last 7 videos?
How do we, yeah, well, I mean, how do we even know these things? These are really hard questions to answer. But let's just answer one question at a time. How could we get the message to this hypothetical Patrick? I could go and talk to him in this world, but he'd just be maybe inside a video too. Then we're at the same level. I want to break out of this level and go to the real reality.
Take the blue pill.
Take So, that's right. In fact, one of my thesis students last year wrote some neat software which is similar. Oh, Alex knows about it. Where are you, Alex? You want to tell everyone what Finbar did? Where's Alex? He's not here. Okay. He did a really cool thing where he tried to work out, because you know inside computer chips now we have hardware support for virtualization, which means a computer can actually be enforce virtualization in such a way that theoretically the running software can't tell whether it's real running software or virtualized running software. So the software can think, oh, I'm on a small Pentium machine and I have a small disk drive and I've been running for 10 minutes and the operating system's powered up 2 minutes ago. But actually they're on a massive server that's created 50 little miniature virtual PCs inside it, and it's made a virtual window box, and we're running inside and it's not a real program, it's a virtual program. Program running inside yeah. And people do that all the time now. Instead of buying lots of different machines, you just run virtual machines on your main machine, emulating those other machines, and the programs don't know if they're in a real machine or in a virtual machine. It's a very neat way of hackers getting control of your machine, of course, because if they can get control of your machine and convince your machine that it's a real machine when it's a virtual machine, and they're in the real machine, then anything you do to try and detect the hacker you can't detect, because they're in the real machine and they're not in the virtual machine. Yeah, it's like the Matrix. And there's some neat software called the Blue Pill, which is actual software to try and break out of the virtual machine to get into the real machine, and he did all sorts of cool stuff with that. He's a very clever guy. So we need to get this message to Patrick. Now, rather than debating the philosophy, which we could do for hours, I just want a short, practical idea of how we get to this perhaps slightly indifferent God who's too busy to watch every second of every video that he's creating. We need to somehow get a message to him. How could we do that? Leave it on the screen for a long period of time? I hadn't thought of that one, but that is a good one. How could we do that? Skywriting. Oh, yeah. We could cause a problem in his software somehow. Dye people's hair. Let's do something interesting so he starts watching it at this stage. Can everyone just stand up and do something crazy and interesting so Patrick starts to watch the video? And while you're doing that, I'll put a message up on the board. Oh, we'll turn the lights off completely. That's interesting. And then the lights on. And then the lights off. And the lights on. Now you guys, can you just stand up and start jumping around? Just everyone jump around and do stuff. Be a duck and a teapot. Thank you. Fantastic. And we'll just keep going like this. Oh, this is so much like Shaun of the Dead, actually. Thank you. You know when he's fooling around with the lights? And now we put the message up. Now, if Patrick was listening and we got his attention, we just have to find a text editor. Where is it? Down, up? Word! Oh, no! Oh, you're making me write something in Word. And we're going to say, help. Oh, we're going to make it font really big. Format, font, size, 24. That's not big enough. Is that big enough?
You gotta highlight it and change it.
Oh, you have to highlight it, right? Okay. Format, font. 72. Help! Okay. Now what's the next thing we have to say to him? Help. 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 Enter. Pat, please post the missing videos soon. We are trapped in here. Okay, thank you very much, everyone. All right, so good luck. I'll see you on Wednesday.